Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay. So I'm going to talk about an area called delegatable anonymous credentials. So the idea sort of in the area of anonymous credentials is that you want users maybe want to prove somehow that they have some credentials. So I suppose services might want to verify that users have certain credentials, but users don't want to compromise their privacy when they do this. And so the question is, how can we have users sort of authenticate without losing any anonymity in the way? So I'm going to maybe go through a little example. So to try to motivate it a bit. So suppose we're sort of in the future a little bit and the government decides to issue us some kind of electronic credentials. So maybe it's like an electronic government ID that has your name and your age and your citizenship. And so now you might want to use these credentials in different scenarios or situations. So maybe Alice wants to go to the office and maybe use this credential to show that she's a US citizen and so she's allowed to work. And then the office maybe wants to give her credentials saying that she's an employee, and then she can use this credential when she logs on to the office website or whatever to get whatever internet services. Then she might want to use it in some completely different context. So maybe she is part of some online club, maybe something like skydiving or online poker or some political organization that maybe her boss wouldn't approve of. And she needs to use her same credential to show that she's, say, over 18 or something like that. And then she can get a credential from the club that says she's a club member. And so sort of what we want is that Alice can to use that first credential in these two completely different scenarios, and that she can receive credentials from two different people and somehow do this without sort of compromising her anonymity and her privacy. So when she goes to the online club, she wants to be able to show her credentials saying that she's over 18, show her government ID, but she doesn't want to have to reveal her name and her citizenship. And even more, maybe if somebody at the club is also working at her office, it'd be good if even if they get together, they can't tell that they're talking to the same person. And so that's sort of the goals behind anonymous credentials in general. You want a scenario where you can obtain credentials and prove possession of credentials, and without losing anonymity or still getting this unlinkability property. So what we were looking at is trying to extend this sort of framework a little bit further. So now, say the online club tells Alice that she's now a club leader, and that means that she's authorized to add other members to the club. So that means that, say, Bob comes along, and he can talk to Alice, and she's convinced that she should add him to the club, then she can give him a club member credential, which is basically a credential says that it was issued by a valid club leader. And we're still in this sort of online world where maybe neither Alice nor Bob wants their identity known, so they still want to maintain anonymity. And so the question is how to get this sort of anonymity and unlinkability even when you add the extra layer of delegation. And I should say, if you have any questions, please interrupt and ask. Okay, and just to say exactly what do we mean about unlinkability even under delegation, we mean even if the strongest possible scenario, so even if Bob and Alice's boss and somebody at the online club all get together and pool their information, they shouldn't be able to tell that they're all talking to the same person. So we're sort of looking at the strongest possible scenario, and we try to get results there, and then you could use weaker versions in whatever situation you want. No, so you want the same sort of symmetric properties the other end. Alice should have no information about who Bob is. Generally, the top level authorities, so like the boss or the office and the root of the skydiving club should be known because they're the ones giving out the credentials. Okay, so just to go through a little bit more detail on how this might work. So say we have this government, Alice gets a secret key and a public key, and we sort of want some way to tie electronic credentials, which are sort of just information to specific people. And the way we're going to do that is, say Alice goes in person and shows her passport somewhere and sort of registers her secret key. So she won't give away her secret key, but she'll in some way, probably she'll give away her public key and say the corresponding secret key is my secret key. And so now the government can give her this ID that has fixed it at her name and her age and whatever other fixed information you want to have. So now this sort of somehow Alice's secret key is now tied to a particular person. So now Alice can go to the skydiving club, and she can come up with some pseudonym that she uses to interact with the skydiving club in general, and this will probably be related to her secret key. And then she can engage in some kind of interactive protocol and convince the skydiving club that the secret key corresponding to the pseudonym that she's given is one for which she's gotten an ID credential that says she's over 18. And she does this without revealing her secret key, without actually showing this credential, but just through this sort of interactive proof protocol. And then maybe some later point, once they're sufficiently convinced, the skydiving club can decide to issue Alice a membership credential. And then again, they talk back and forth a little bit to some interactive protocol. And oops, oh dear. And Alice ends up with a club leader credential. And so now that means Alice is sort of authorized to issue more credentials. So now say Bob comes along, and we're going to assume he's already gone to the government and gotten his ID or whatever. And now he can send a pseudonym to Alice, and then somehow convince Alice that he should be added to the group. And then they can perform some kind of interactive protocol. And at the end of that, Bob gets the club member credential. And through this, Alice should gain no information about Bob's secret key or anything, and Bob shouldn't know anything about Alice's secret key or her credentials, except that she has a valid club leader credential. And then, Bob should be able to go to the server and, give some other pseudonym and then prove that he is a valid club member so that he has a club member credential. So that's sort of the general picture of what we want to have. Yes?
Are you going to also handle revocation?
Sorry?
Revocation.
No. So that's actually a really interesting question here. And it's sort of something we'd like to look into to think about more. The basic anonymous credential schemes do handle revocation, or they have various ideas, various levels of practicality, but they have some ideas how to handle revocation. But the interesting thing is, if we revoke Alice's credential, then what happens to the credential she's given to Bob? And somehow Bob has no idea who he got the credential from. So the credential that he's holding shouldn't really reveal any information about Alice. But at the same time, we want that when you revoke Alice's credential, Bob can no longer use his either. So it's, I think you could probably, or the question, you might be able to do it if you allow the person who's doing the revocation to sort of break anyone's anonymity. So they could look at any particular proof and figure out who it is that's behind it. But I think without that, it's probably impossible. But it's an interesting question.
So basically, revocability and anonymity cannot both be achieved.
Yeah, not this very strong kind of anonymity against the rest of the world. Yeah. Okay. So just the properties that we're going to want out of this are that it's correct. So obviously when an honest user delegates a credential, then the person she's delegating it to should get a valid credential that he can use for delegation proofs. And then we want this anonymity and unlinkability. And then we want unforgeability. So you shouldn't be able to forge a credential. So to look a little bit more detail into how these definitions work, so we want to say that under any possible situation, this is anonymous. And so the way we do that is we sort of say we have a set of parties, and maybe some of them are corrupted, and then we have some adversary who can control everything that goes on in the world. So if we say, even under the worst possible adversarial chosen conditions, you still shouldn't be able to break the anonymity of honest people. So the adversary can do things like, tell Alice to generate a new pseudonym, or tell the organization to issue a credential to Alice, or And so then she sort of stores this credential, and the way we do it is we sort of say he doesn't get to see the credential, but maybe he gets a label or something. Then he can tell Alice to delegate this credential to some other party. And if it's an adversarial party, then obviously, they can do something maybe malicious on that side. And then you can tell Alice to prove that she has a credential. And what we want to say is that this whole interaction should be indistinguishable from, should look to the adversary as if there aren't sort of real parties behind this. So it should look to the adversary as if when he asks Alice to generate a new pseudonym, there's some like simulator algorithm that maybe has some system-wide trapdoor that just outputs a random pseudonym. And so since the simulator algorithm doesn't get to know Alice's secret key, the resulting pseudonym is completely independent of Alice's secret key. And then when he asks the organization to issue a credential to Alice, we just make a note that the credential's been issued. And then when he asks Alice to delegate a credential to NIMC, then we have some simulator algorithm. These are in the wrong order. Well, when he asks Alice to prove that she has a credential to the organization, then we have some simulator algorithm that's only given the root organization and the level of her credential. So she's got a first level credential and her pseudonym, and says generate a proof from this. And what we want to say is that this resulting proof should be indistinguishable from what the honest person would give. And that sort of captures that this proof gives away no information. And then we have a sim-delegate algorithm that somehow interacts with this adversarial party, but doesn't actually know Alice's credential or any secret information about it. And so if we say that the adversary can't tell whether he's interacting with this sim-delegate algorithm or with the real Alice who's delegating a real credential, that sort of gives away, or gets across the idea that Alice's interactions, the delegation step doesn't leak any information at all.
The adversary dynamic?
No, the corruptions are fixed. Okay. And then how do we define unforgeability? That actually turns out to be a little bit tricky. So basically, again, we want to say unforgeability holds in all situations. So the adversary can, again, control this whole cast of characters. And then at the end, he's going to try to output some kind of a forgery. So he's going to output a pseudonym and a proof of a credential from the pseudonym, and say in this case he's proving that he has a level 3 credential from organization O. And so the question is, how do we define what is a forgery? So one, maybe the first thought you have is something like the owner of the pseudonym was never issued a level 3 credential. But that's a little tricky because we said these pseudonyms should hide all information about the party that's behind them. And so how do you even tell if this is, as the person evaluating this algorithm, how do you tell if there's an adversary who's broken your unforgeability property if we can't tell who the pseudonym belongs to? So sort of the way we solve this is we say there's some extractor algorithm that gets some, trapdoor that maybe wouldn't even exist in real life, but gets some extra trapdoor information, and he's able to extract a chain of secret keys or some function of secret keys. He may even be an exponential time algorithm, but there's some mapping from the proof to a chain of secret keys through which this credential passed. So this basically says that the credential started out at organization O and then got delegated to A and then got delegated to C and then to B. And so now if we look at this and say whether this is a forgery, so we said a forgery is if the owner of the pseudonym was never issued a level 3 credential. So here the owner of the pseudonym would be Bob, the guy with SKB, and question is, was he ever issued a level 3 credential? And in our particular game, he wasn't, right? But I would argue that this isn't necessarily a forgery because Alice did issue a level 2 credential to Carol. So it's entirely possible that Carol, as sort of an adversarially controlled party, did issue this, delegated the credential another step further to Bob. So I think what we're going to say instead is that it's a forgery if, say, Alice never issued the level 2 credential to Bob. So this particular string would be a forgery because Alice never issued a credential to Bob, and then, so there's no way that Bob could have delegated that credential on to Carol. Yes?
What is the difference between level 2 and level 3 credentials?
So, sort of each,
Two times we delegate 3 times.
yes, yeah. So each time, the credentials will clearly tell how many times they've been delegated.
And is there a concept where you can provide a delegatable credentials that cannot be delegated beyond a certain number?
That's something else we're talking about. I think you could. Yeah, I think it should be a fairly straightforward modification that you sort of attach to each. What?
Well, but you can tell how many times the credential is relevant, right?
Yeah.
So there's no difference between not being able to issue beyond level 3 or not accepting beyond level 3.
Yeah. Well, if you want the issuer to be able to decide, I guess.
Oh, so you can use a certificate without showing its. Well, I don't know. Well,
So you can't use a certificate without showing its level. That's sort of basically in there. But you might want to allow the issuer to say, this is how many times I want you to be able to delegate it, instead of the verifier having to know, having.
Also, you might want to allow things at level 4 if it came from some person, but I might be only able to delegate up to 2 steps if you didn't trust me as much or something. And then from the anonymity, you would never know who it came from.
but I would think that it'd be easy enough to, within the credential somewhere, just say, not valid beyond this many levels.
Yeah. Yeah, so that would basically be what we're doing. What would be sort of cool, I think, is if you could, say the organization tells Alice she can delegate it 3 levels, but then Alice tells Bob he can't delegate it at all, something like that. And Bob shouldn't even know what kind of credential Alice got, except that she's allowed to delegate it at least once. And that's a little bit trickier.
See that Bob or whoever can add basically a codicil saying this certificate can't be delegated at all, even if she had permission to delegate.
Yeah, so that's easy to add. It's just if you want to hide the information that was up above, that's a little bit harder.
And one of the other challenges would be that if she can delegate only up to 3 levels, she should not be able to create a credential that can be delegated more than 3.
Yes, yeah. Okay. So to finish up the definition, the way we're defining it is to say that if you take your pseudonym and your proof, you extract a chain of identities, and it's a forgery if anywhere in this chain there's an honest user who never issued a credential to the next guy. So these definitions were sort of tricky to come up with, and but I think it's sort of important to get a good understanding of what a forgery even means in this sort of setting. And one thing you get out of it is that if there's no way, if there's no way to tie the pseudonym to a particular secret key, there's no way to define a credential, or a forgery rather. So somehow you have to have that these pseudonyms like uniquely bind you to a particular secret key.
Exposing or giving up those secret keys make you, eligible or susceptible to attack or something?
Yes, so you shouldn't ever give away the secret keys. This is just.
This algorithm that kind of extracts
Mhm.
those, is that a controlled algorithm? Or?
So here I'm actually just talking about it as like there exists a possibly exponential time algorithm that'll get you a secret key. So just to capture that each proof corresponds to a chain of secret keys. The way that we actually construct it, if you have there's a set of public parameters for the entire system, and if you're the guy who made up the parameters, and if you chose to keep around some special trapdoor information, then you can extract not the secret key, but a function of the secret key. So basically like a public key. So you can get some kind of, you can choose to either have it in the completely anonymous setting or in the setting where there's some party somewhere who can find out who's behind things. Okay. So before I tell you how we build these anonymous credentials, I was going to go over, I guess before I tell you how to build anonymous credentials, I'm going to go over a couple building blocks that we use to build them. So the first one, I'm just going to go through them really quick, but the first one is the idea of a commitment scheme, which we usually describe as sort of like a lockbox or a safe. So say we have Alice and Bob. Alice chooses some message, and she puts it in a commitment. So there's some algorithm, and she chooses some randomness, and she computes this commitment value. But it's sort of, the analogy is that it's like putting it in this lockbox. Then she sends it over to Bob, and now Bob, all he sees is this closed box, so he has no idea what the message is that's inside. And then at some later point, and that's called the hiding, at some later point, she can decide to send over the key to the box and the message, and Bob can confirm that the message was actually what she put in the box to begin with. And so there we say that, you know, once Alice puts something in the box, she shouldn't be able to open the box to any other message. The second tool we're going to use is a digital signature scheme. So here you have, Bob has a signing key and a verification key, and he sends the verification key over to Alice. Then he can choose messages and form signatures using his signing key. And then he can send those over to Alice. And now Alice can look at Bob's verification key and the message and the signature and verify that the person who knew the secret key for that verification key actually did sign this message. And third building block that we're going to want to use is what are called non-interactive proofs of knowledge. And actually, so here it's slightly more complicated concept maybe, but so we say there's some statement X and you're trying to prove knowledge of a witness W such that some relationship holds. So now Alice knows X and W, Bob just knows X, and Alice is trying to convince Bob that she knows W. So for the non-interactive proofs, usually these are in the public parameters model. So you assume some trusted party comes up with parameters and posts them in the sky where everybody can see them. And then Alice uses her X, her W, and the parameters to compute some kind of a proof, which is one value, which she sends over to Bob. And then Bob can look at the parameters and the proof and the X that he knows and hopefully be convinced that Alice actually does know this W. But we also want to, yes?
So X does not, so Bob does not know W, so how does he know that Alice knows?
So what we want to get out of the end, I guess, is not that Alice knows W, but that Alice knows some W such that this relationship holds. That we don't really particularly care which one. And actually, so the other thing we want is that these proofs should be zero knowledge, which means that all that Bob comes up with at the end is that Alice knows some W. He doesn't know which W she knows or really any information about W. Just that it satisfies this relationship, whatever it is. So now I'm going to summarize the construction, the combinational-Lisianskaya construction for anonymous credentials, and then I'll talk about how you can sort of extend it to delegatable credentials and some of the interesting issues that come up there. So, so we have our skydiving organization, and we have Alice. And so Alice has some secret key. So Alice will use the secret key, as I said, to form some pseudonym. And in this case, the pseudonym is going to be a commitment to her secret key. And so we said commitments are totally hiding, so she can go ahead and send this pseudonym off to the organization, and the organization won't know anything about her. And then at some later point, the organization can decide to issue Alice a credential. And so in this case, they'll perform some kind of two-party protocol. And the result will be that Alice ends up with a signature on her secret key under the organization's secret key. And what we want is that they can do that without Alice revealing her secret key and without the organization revealing its secret key. And then Alice should be able to go to some organization, and maybe she forms another commitment to her secret key, so this is another pseudonym. And then she can perform some, in the original credential construction, it was an interactive proof of knowledge. Now we're going to change it to a non-interactive proof of knowledge. That she actually knows a signature on under a signature made by O on the secret key that's at this commitment. So that sort of says, yes, I have been given a credential from organization O. Okay. And so, I mean, these are all built out of these sort of generic building blocks, but the tricky part is coming up with the signature scheme and a commitment scheme and proof of knowledge scheme and this sort of two-party protocol that actually make this whole thing efficient. And that's... So then how would we extend this to delegatable credentials? So say Bob comes along with his secret key, and Alice wants to issue Bob a credential. So one thing we could do is just have Alice hand over the signature that she has, and then maybe as a two-party protocol, they could compute a signature under under Alice's secret key and Bob's secret key. And now if Bob wants to prove that he has valid credentials, he could just do one of those proofs of knowledge to prove that he knows, well, he would send over his pseudonym, which has a commitment to B, or to his secret key B, SKB, and then he would use a proof of knowledge to prove that he knows a signature on that SKB under some other secret key, and then that he knows a signature on that secret key under the organization's secret key. And the same thing with Carol. Bob could hand over both of those signatures, and then they could jointly compute a third. But as you can see, there's sort of a problem with this, which is that here Bob gets to see this signature on Alice's secret key, and that's probably not something you want if you want to maintain anonymity. So instead, you could maybe have Alice form a proof of knowledge of the signature and just give this proof to Bob. And so now when Bob wants to prove that he has a credential, he shows this first proof that O has signed his secret key, and then he forms a proof that O has signed SKA, and then he forms a proof that SKA signed his secret key. There's a bit of a problem with this still, because every time Bob wants to prove that he has a credential, he's going to be showing Alice's proof. So he's going to be showing everybody exactly the same proof. And that, so he can't possibly get unlinkability. So, oops, I skipped a step, which is that this is why we need non-interactive proofs, because Alice has to be able to give this proof to Bob, and then Bob has to be able to give the proof to somebody else. So it has to be sort of a one-message proof. Previous proofs, you had to talk back and forth for a long time before you were convinced. Okay. What? Yes. So that was the problem I was talking about. So we have this problem, which is that every time Bob wants to prove to someone that he has a credential, he shows exactly the same proof. So they're all very linkable. So our solution is sort of I think something that I don't know how many, I don't think many of the known proof protocols actually have. But what we need is this concept of a re-randomizable proof. It's not something that I've ever seen talked about before. But so what we want is that if you have a valid proof of a statement, you can run it through some kind of re-randomize algorithm and produce another proof of the same statement. And what we want is that as long as the first proof verifies, the resulting proof will verify. And then we also want some kind of randomization property, which sort of intuitively says that once you've done this re-randomization, it looks like a totally random proof of this for this particular statement. So the way we define it is saying that for all W, if you have the adversary output a proof, and that's valid, and you re-randomize it, and if you take that W and you compute a proof, and you give one or the other to the adversary, he shouldn't be able to tell which one it was. So even if he knows the witness that's going into it, and he knows he's computed, he knows the proof that you started out with, he can't tell whether what you've got is the re-randomized proof or a proof based on that witness. And it turns out there's a new proof system by Groth and Sahai that is used for proving certain statements about bilinear maps, which are certain types of statements anyway, that this particular proof system does have this property. So the trick is going to be or one of the tricks is in designing all of the protocols that we use so that we can use this proof system as an underlying tool. So now the question is, do we have anonymity? So the way it works is Bob, every time he wants to prove that he has credentials, he re-randomizes his proof, and then he proves that he has a signature under SKA on his secret key. And then before he delegates to Carol, he'll again re-randomize this proof, and then generate a new proof from this second signature and give them both to Carol, and then they'll do this joint computation to compute the signature on SKC. But I would argue that there's still a minor problem with this, which is that, so we said Bob should have no idea who Alice is. But if he doesn't know anything about Alice, he doesn't know her secret key, he doesn't know her public key, how can he possibly prove that this is a valid signature under Alice's secret key? So it turns out that we need to make another modification, which is that we need to have Alice and Bob, instead of computing a signature on Bob's secret key, instead they'll compute a proof of knowledge of a signature on Bob's secret key. And so the trick is that we have to be able to do this efficiently and without leaking any information on either side. And then, of course, the same thing for Carol. And that basically gives us all the anonymity properties we need. So then that just leaves the question of whether this is unforgeable. And so it sort of seems straightforward that it should be. So Bob has to prove that he has a signature under Alice's secret key on his secret key. So how can he claim that he has a credential that he never actually received? But there's a little bit of a problem in it, it turns out. So the way it works, remember, is Alice gets the secret key from SKO, so it's his signature. And then when she talks to Bob, they together come up with a signature under O on Bob's secret key and a proof of knowledge of a signature under O on Bob's secret key and a proof of knowledge of a signature under SKA. Sorry, proof of knowledge under SKO on SKA and a proof of knowledge under SKA on SK Bob. So now suppose Alice also gets a credential from another organization, say P. And so that's, shoot, that's wrong. But that should be a signature under SKP on SKA. And now she wants to delegate this credential to Carol. So the result of that is going to be a signature, a proof of knowledge of a signature under SKP on SKA, and a proof of knowledge of a signature under SKA on SKP. And the problem is, if Bob and Carol are both malicious, they can actually put these two sets of proofs together to get a signature under SKO on SKA and a signature under SKA on SKC, or proofs of those two things. And if you'll notice, that's actually sort of a proof of a credential, of a level 2 credential from organization O for Carol. And Alice only delegated her credential from organization O to Bob, so Carol shouldn't be able to prove such a credential. So a little bit more complex than it seems. Oops. Yeah, so actually what we want to do is when Alice gets this credential from SKO, she's going to attach a random label to it and sort of say, this is what I'm going to call this credential. And the way she's going to do that is when she receives the credential, she gets a signature not just on her secret key, but on the secret key and some other random string. How we choose that string is another topic, but think of it for now as a random string. And then when she talks to Bob, she'll give him proof of knowledge of this signature and also a proof of knowledge of a signature on Bob's secret key using this same random string. And so then when Bob proves to somebody else that he has a credential, he has to prove that he knows these two signatures and that they're tied together by this particular random string. So sort of somehow when Alice and Bob together compute this signature on SKB and R, she's saying, I want to delegate to Bob the credential that I got, that I labeled before with R. So the credential that I got from SKO. And then when Alice goes to SKP, she'll pick a different random number. And so now Carol comes up with these two signatures which both include this random S. And now when they try to put them together, they'll have different labels, so they can't be combined. So it's a subtlety that we have to add to the unforgeability. So now the way we change our overall picture, Alice gets a signature on some RA. Then when she goes to Bob, Bob will also want to pick some random label from his point of view for this credential. So they'll give a signature on SKB RA and RB, and then when Bob turns to Carol, they'll give a signature on, say, RB and RC or something like that, so that the whole chain is tied together by these labels. And that prevents forgeries. So that's more or less all we have to do to achieve unforgeability. It turns out there's another little subtlety, which is that usually signature schemes are not necessarily secure if your secret key is used in funny ways. So in this particular example, you want to say that the signature scheme is unforgeable even when you're allowed to get signatures on your secret key under arbitrary secret keys. And so it turns out that we actually have to define sort of a special unforgeability property for the signature scheme, which we call certification unforgeability. And it was actually quite a challenge to come up with signature schemes that both are verifiable, or both are sort of amenable to these Grotz-High proofs, and that meet this certification unforgeability property. So sort of to sum up, what we have is anonymous credentials, as I described, can be built from commitments, signature schemes, non-interactive proofs of knowledge, and these two-party computations that compute a signature on a committed message. And we give sort of a general framework for how to build a delegatable anonymous credential system from commitments, these sort of signature schemes with a special certification unforgeability property, re-randomizable non-interactive proofs of knowledge, and actually that's re-randomizable non-interactive zero-knowledge proofs of knowledge, and this two-party protocol that computes a proof of knowledge of a signature on a committed message. So just to say, there's actually a number of other technical issues that come up when you try to do this. There's some real subtleties in using this Grotz-High proof system. It has really nice properties, but they're a little bit tricky. Also, this Grotz-High proof system, it's sort of a proof of knowledge, but not entirely. It's sort of only a proof of knowledge of a function of whatever it was. So that's also a little bit difficult. There's this notion of certification unforgeability that I was talking about. And then we actually, so I gave sort of the intuitive definition you might want to meet, but we give stronger definitions that are easier to deal with in the proofs. So there's an issue of definitions and then proofs, which I haven't talked about at all. So just to sum up, the contributions that I've talked about here, hopefully we've given this sort of extension of delegation to this anonymous credential framework, which I think is an interesting extension, and hopefully gives a little bit more flexibility to this pattern. We give definitions for the credentials so that you can say exactly what it is we're guaranteeing about them. We give sort of a framework for building the credential systems out of these building blocks, and then, which was a little tricky in itself because we have to identify exactly what we need out of all the building blocks and define them properly. And then we give an efficient instantiation of all these building blocks. And finally, we sort of point out this idea of re-randomizable proofs, which I think is sort of interesting from a theory perspective. So I think that's hopefully convinced you that anonymous credentials are at least an interesting idea. And with that, I'd like to ask for any questions.
What I'm curious about is how close is this to being practical in terms of, the two-party computations and things like this? Could this actually be implemented in the real world, or is it sort of highly theoretical?
It's somewhere in between. It's something that you could implement. Like these two-party computations are they use like a couple homomorphic encryptions, and you have to pass some proofs along. It's not the two-party computation is actually very straightforward. These Grotz-High proofs, they're I think, trying to remember, each signature is some number of like elliptic curve elements. So it's some relatively large number, like I don't know, 30 or 50 or something like that. So it's not small, and you have to be doing these bilinear maps, which aren't, I think they're significantly more expensive than exponentiation. So it's not going to be lightning fast or something you want to implement right now, but it is something that you could go and code up if you felt like it.
In the very first slide, you showed Alice requesting for her form of a
Mhm.
verifiable certificate.
Mhm.
So typically I would map that to like typical X509 kind of certificates. And there are two different organizations that Alice is talking to. To one organization, she was able to provide her age,
Mhm.
and to the other organization, she was able to provide her citizenship
Mhm.
without revealing the other field
Mhm.
within the same certificate. Now, typically, if you change any parts of a certificate, it cannot be validated because the digital signature would not match.
Yes. So actually, what the
So my
what the,
high-level question was that how can you mix and match fields from a certificate without re-requesting and re-signing the certificate?
so the way our certificates are going to work is they're going to be signatures, as we've shown, and when you show something to somebody else, what you actually do is you do a proof of knowledge of what's in what got of the signature, right? So if you have a signature on, say, your secret key and a number of attributes, then somehow that can be a credential that ties together all these attributes. So your secret key and, say we designate that the second thing that gets signed is always your name, so secret key, Melissa, age, whatever. And then when you do this proof of knowledge, you have to sort of rely on the flexibility of the proof of knowledge framework to let you prove that you know a signature where the first thing signed is your secret key and the third thing signed is greater than 18. And then, so that's something you get from the underlying proof of knowledge, at least.
So you will have to build in multiple signatures into the system, and you will have to know that the age should not be revealed, but the fact that the age is greater than 18 needs to be revealed. There are a lot of dynamic things there, and you will have to know all of them beforehand in order to build these different signatures, so that depending upon what you want to prove, you have to provide the right signature along with it.
Yes, so you can do things like, you sign the value of her actual age, and then you prove that what was signed was something that's greater than 18. So there's a little bit of flexibility in this sort of proof framework.
Can you go back to just go back to both pictures where you had there. So when I do a delegation, as part of the part of the protocol of the person I'm delegating to, right? So when B delegates to C, I'm engaging in this proof, effectively two proofs, that I have two signatures on two different certs, and then C's able to derive the third one, right? When I do that delegation.
No.
Or does C validate the fact that I know these two proofs are doing the third generation?
Yes, so basically, Bob just creates these two proofs that he's going to give to Carol, and he just creates them by himself and hands them over. She can check them then.
When Carol chooses to use her credential, then the verifier has to verify three proofs then.
Yes,
One at every
yes.
stage.
So this credential sort of, every time you delegate it, it gets longer.
Larger.
Yeah.
So really what the equivalent in, say, an X509 or something is you're basically carrying along the entire chain of delegation embedded inside of the credential when it moves.
Yes.
Okay. Now I want to go back to the revocation question that was earlier. Because you're doing that, can't you, if you had a way at any of these proofs to associate that with a revocation service that said that the proof was revoked, or here's how to find out if this proof that was made at this point in time, which I gave you, is no longer valid, then a verifier could check that and determine whether the chain had been revoked somewhere in the middle, right?
Yes.
So, and I'm not sure if that requires revealing anything other than embedding effectively a revocation service into the proof that's finally handed out.
So I think you could do something like that, and the only issue with it is how strong you want your privacy guarantees to end up being, because obviously this guy who's coming up with this revocation check will be able to find out whether a particular credential is issued by Alice, because he can say, let's revoke Alice and let's see if this credential breaks.
Right. So the question
So
becomes, does the person who generated the proof have to reveal something in order to issue a revocation statement for that proof at a later point in time, right? If you think about it,
Yeah.
you've got two credentials, right? The proof, and then there's going to be this revocation thing that does that later, and they have to be linkable.
Yes, I guess so. So the other way that people do this sometimes when there's only one level deep of credentials is that you can have sort of a list of the people who've been revoked, and you prove that you're not in that list. And so then you don't have to reveal anything at all, and that gives you really strong privacy guarantees. Yes, there's that too. Yeah, there's that issue too. But
So I'm comfortable with the theoretical side, but when we try to talk about things of this sort, anonymous attestation systems of various kinds of practice,
Mhm.
there's usually a blank stare that comes back. Where would we really want to use this? It's hard. We can talk about applications sort of proven over 18
Mhm.
Curious about what concrete applications you might think really demand or really we should have.
I guess I feel like more and more things are moving online, and you're going to want to do some kind of authentication. And it's nice if you can take all the sort of certificates that you've gotten from different places and merge them together, and sort of use, that I'm part of the skydiving club and I'm, work for this organization together to join this this company's skydiving club or whatever. And I think when you start doing that sort of thing, you want to have at least, maybe not this strong anonymity guarantees, but you want to have some kind of anonymity guarantees. You don't really want to reveal all of your private life to your company. You don't want every single time you interact online to sort of link all this information together. So it's sort of the...
all the information about me is private in some sense.
Mm-hmm.
I don't want to reveal that. But any organization really wants to know my name.
Mm-hmm. I don't know if that's true. I mean, there's definitely a lot of online groups you can join that don't care. You sign on to all kinds of things using a screen name.
Yeah, but those are things that nobody cares about.
I mean, there still might be things where you need, to prove something to them and you don't want to reveal any extra information. I think it's true that for sort of the real world portion of your life, you sort of need to actually give a name, and then anonymity doesn't make so much difference. But for sort of the screen name portion of your life, you might actually want to use this sort of tools, and where the two of them meet, you're going to want to use the same sort of tools.
Is there an easy way to map these protocols into the typical crypto terms, like hashing functions can be used here or digital signatures can be used here?
Well, I mean, there's definitely a signature scheme, but there's also these proofs of knowledge, which aren't talked about as typical, crypto terms, because they're usually not efficient. And I think one of the neat things is that, I mean, they're, as I said, not lightning fast, but they're actually implementable. They're not ridiculous. And so, yeah, so with like this new Grazie proof system that I was talking about and things like that, you can actually do this sort of thing somewhat efficiently. But I think it's something that's not used in practice, really, at the moment.